Hi students, welcome back. In lab 4 today we're going to talk about taguchi air. In lab 5, just to give you a preview, it's going to be called taguchi air 2. So intuitively, taguchi air 1 and 2 are going to be built upon each other. So it's very important that you try to understand what we're doing today and why we're doing things we do today, because in next week for lab 5 we're going to directly take what we have done today, and assuming everybody has understand it well and done it right, and then to build on top of that for more difficult and intricate functions in Excel. So today, the other reason why we're doing the taguchi air 1 and 2 right now in this week and next week is because it's going to be a nice overview and preview for your final project. In many aspects, they're connected and are very similar. So the skills and you're learning today and next week, as well as the team forming and working experience with all the team members that you got this semester, it's going to carry through with your final project as well. So it's very important that you, if you haven't already done so, to start get to know your team members' working styles, each other's strengths and weaknesses well in these two group assignments for taguchi air 1 and 2, and then so that when we are carrying on to a more intense phase of the semester, you won't struggle to take more time and effort to figure out who should do what part. So as I've mentioned, this lab is a group assignment, so try to have one team member designated to submit the file through Canvas after you guys are done to be graded, and try to have the same team member do the same thing for taguchi air 2 next week. The reason why we're doing this is because we really are only grading one assignment for the entire team, and everybody on the same team is going to receive the same grade at the end. So if having one representative is just making things easier and making sure that this person is submitting the final copy representing everybody's work on the same team. So for this assignment, all the formatting requirements from the previous Excel assignments still hold, but the only difference is that this is a more hands-on lab than the previous ones. I would say usually what students do is that the first half, they literally do hands-on experiment inside the lab room and outside in the hall, which I will talk about later. And then the second half, they bring back their experimental data that they have collected outside the classroom, and then put it in Excel and start analyzing them. So one tip I would like to offer you guys is time allocation. We have experienced previously some students not having enough time to finish everything that's required in this lab because they either spend too much time outside tossing the airplanes and experimenting and leaving very little time to complete the Excel, or flip-flop. They didn't do the experiment correctly or very well in a very short period of time, and they ended up having to go back again and redo it. So in order to prepare yourself, I hope you pay attention to the video and get yourself as prepared as you would like and as prepared as you can before you step into the lab room. So we'll dab right into it. If you will, flip to page 473, and it should show you a template of the paper airplane. I trust that some of you guys have had experience folding just an airplane when you're little, probably just flying them around. So if that's the case, it's great. That means you already understand, hopefully, how to fly an airplane, how to throw it, how it feels to manufacture it. But if you haven't gotten that experience, which has happened in the past, an entire team wouldn't have anyone that has had experience folding an airplane or tossing one before, that's completely okay. We will provide the templates to you guys, so you don't have to actually bring copies of the templates to the classroom. But what you need to bring is tape, just regular, either carpenter's tape or clear tape, or anything that could do as a place marker on the tile without actually marking the tile, and then paper clips to serve as the weight location on the airplane, which I'll talk about later. So as you start the lab, if you have questions, ask away. If not, you can bring your team members out to the hall. If you try to imagine that you're going out of the lab room, the hall is on the left. So on the left is Department of Industrial and Systems Engineering. On the right side, it doesn't belong to us, so please don't invade other departments' territory. We usually just keep the experiment going on the hall on the left side. And try not to throw it to the downstairs area. Try to pick an area that's enclosed and safe to fly, so the plane wouldn't get stuck on lights or anything that's hard to get or create a fire hazard. You can pick anywhere you want to in the hall, in the correct side of the hall, and use the tape to tape down a specific spot where you would like to fly every single time. So, but before you do that, you will need to fold the 9 different designs of the paper airplane, which I will show very quick right here. So on page 471, it shows you the 9 different types of planes, which are marked here as experiment number. That's the 9 different airplanes you will fold from airplane 1 to airplane 9. And how they're different is that on the template, it will show you where different options are. So for the weight location, there are 3 different locations for them where you can clip your paper clips on. And then for the stabilizer setting, there are also 3 options where you can fold. The 3 nose lengths, which you can also fold differently, and the wing angles you can toggle by folding at different locations as D1, D2, and D3. So if this is somehow very confusing to you and you can't figure out how to fold them, that's okay. We'll have someone, hopefully some other person from a different group can show you how to fold that. So once you understand where your plants are, I think it has worked pretty well in the past that the group would have 1 or 2 people stay in the lab and start constructing the shells of the Excel tables, because the templates of the tables are actually grabbed from the book. So for example, the first one you're going to have is a summary table of your data collection from outside. So that's on page 471. And then this person can already construct the shell of this table. So once your team members on the hallway comes back, they'll just punch in the empirical number right here. So that's the flight distance of each and every plane flying for 9 different repetitions or 9 different times. So once you have that, that will be easier for them to just punch in the numbers. And same with this one, like all of this is actually in the book. So you should have that shell of the table ready, and then when the numbers come in, they'll just go in the right locations. So we'll talk about the technicality of the tables now. If you are flying in the hallway, you will notice that the tiles are of a uniform size of 1 foot times 1 foot. That's also 12 inches times 12 inches. We're not going to ask you to bring a tape measure or a walking meter with you to measure as accurate as I did right here, which I have a walking meter with me, so I can do much more accurate than just by looking at it. But when you're doing it, I want you to do it quickly but somewhat accurately. So make sure that you round the distance to a half foot. So what I mean by that is that if, for example, your plane flew 20 tiles of distance and over, but not so much as occupying the entire last tile, it's a little bit short, then that's probably, for example, this one right here, 20.9, you can round it to 21. And then if it's right at the half foot at the end, you can just say it's 20.5 feet. And if it's somehow less than half a foot, say it's about 21.1, you can just say it's 20 feet. So if this is somehow confusing, I can talk about it in the lab as well. But that's the gist of it. You're going to fold all 9 airplanes, and then for each and every one of them, you can throw them 9 different times, just like this, and record their distances accordingly. After you have done that, you should have 9 times 9 equals to 81 data points right here as I have highlighted. After you have punched these numbers in, we're going to calculate the statistical properties of each and every plane across their different repetitions of throws. So what I mean by that is the mean distance and standard deviation are 2 statistical properties that are very basic but are very fundamental to a course hopefully you will take later that's called probability and statistics. And these are the 2 terms I think the professor will talk about in the first couple weeks of your study because they're very important and fundamental. What I mean by mean distance is that the 9 different times where you threw your first plane, they probably landed at different locations because not every one of your throws is going to be hitting the exact same spot. So the distances are naturally going to be different, but by calculating the average of these 9 distances, how we do that is we add them all together, the 9 numbers all together, and we use the summation to divide it by 9, and we would get the mean. So the mean distance, in other words, is also called average distance. Getting that, you get an idea of, oh, okay, well, I fly them many times. They don't necessarily hit the same spot, but it's about, 22.1. It's just about that. Maybe a little lower, maybe a little higher, but right around that. But the mean distances, though useful, sometimes can be misleading. If your airplane the flight distance is not very stable, let's say one airplane flew 2 feet, the other airplane flew 38 feet. So 2 plus 38 is 40, and 40 over 2 divided by 2 is 20. 20 as a mean distance looks okay. It's pretty normal. But is it really though? Maybe not, because the results are actually very polarizing, but they're polarizing in a way that when they average, they cancel each other's effects, polarizing effects. So that's not very accurate in terms of just caring about the mean distances. That's why we needed the standard deviation. And the standard deviation measures the dispersion and, in other words, polarization of the data. So if I had a 38 feet and 2 feet, my standard deviation is going to shoot up high. That indicates my flight distance is not as stable as I would like it to be, and it doesn't really hit around the same mark very closely every single time. There's some big differences between the flight distances. In this case, what we call a good quality airplane, in this experiment, we want the standard deviation to be low, meaning that the stability of the flight distances are high, that every time we throw a plane, we want it to be hitting around the same mark, even though some deviations can be allowed. And then the mean distance, we want it to be as high as possible. So we want the flight distance to be as far as possible. So that's how what we define a good quality airplane in this assignment. So how we do that is for mean distance, you can punch in the Excel function equal to average and parentheses across all 9 cells right here. So B8 is right here, and then J8 is right here. You just drag them across, meaning that you're averaging across these 9 different numbers. Standard deviation, you punch in equal to STDEV, parentheses, the same thing. You can drag the, okay, I made a mistake here, fix it. There we go. So you can drag the cursor across repetition 1 to repetition 9, and then use the fill handle to fill it. There we go. So we got the standard deviation, we got the mean, and then we're done for the first sheet. Moving on to the second, I think you will see the template of this table in the book, or you can just watch the video and do the same thing as I did right here. What we're going to do is that we're going to organize the data a little bit differently. We don't care so much about the individual flight distances anymore. All we care about is the mean distances and standard deviations we have just calculated. So moving them to the right columns of here does it. We'll complete this table, and then what the A, B, C's, and D's are doing here is it's indicating the different designs. Hopefully how you have constructed the plane is how the order that you threw them. So for experiment 1, we're referring to the first row here, meaning the first airplane. So the design is weight location at A1, stabilizer at B1, nose length at C1, and wing angle at D1, and so on and so forth. This is just a different representation of the data we have picked from the previous table, and we're organizing it differently. After you're done with this, we're going to talk about pivot tables. Pivot tables are one of the most important functions of Excel. It allows you to pick only the important and relevant information from a larger and more intricate data set. So you can screen out all the information you don't want, and you can only display the information you wanted to display and you care about. So in this case, we're going to construct 4 different pivot tables as shown here. So how we're going to do that is we're going to select all the cells in this table except for the column 1, and press data and click on pivot table. After we're done with that, a menu will pop up and it will say use the table range in this workbook, and you can tell that it's already indicating the area that we have selected. Choose where to place it. We want to place it in the same worksheet, so we click on existing worksheet. I won't go ahead and do all 4 of them, but I'd be happy to show you an example. So we'll take wing angle as an example. So let's see that if I want to put this pivot table around wing angle in here, I will click on E38. It will show up here and I'll say OK. After that, another menu will pop up. As you can see, our pivot table's form is already here, but it doesn't have anything in there until we click the relevant selection. So we'll click wing, mean, and standard deviation. After I click on that, some numbers are filled in, but it doesn't look exactly right. So we're going to move the first thing on the values, how do you say that, the table right here, move it to row labels. And then after we do that, it looks similar to what we wanted, but some of the things still need to be changed. For example, the values, we don't want the sum of means. What we wanted is the average of means. Because if you look at the wing angle, and we're only caring about wing angle in this pivot table, we wanted to know the average across, for example, wing angle at D1. We wanted to know the average of these instead of the sum of them, because the sum of them is a clump of the flight distances across D1s, but it's not as informative as an average, so we're going to change that. By clicking on this information button right here, we're going to change it to average. So is this one. I'm going to change it to average. And there. There, we're almost done. We can click off of this. Change the setting a little bit because I'm really not a big fan of this background. I'm going to go change to a clearer and cleaner background and add borders to it. Now, it looks good, but the decimal places seem to be a little too much. So we're going to have only 2 decimal places in the pivot tables. The row label, we need to change that to wing angle so whoever's reading your table is able to understand that you're constructing the table only around wing angle. And when wing angles at D1, D2, and D3, you can pick out the highest mean because that represents the highest quality in terms of average of means. And the average of standard deviation, we want it to be low. So that seems to be right. And then so we want, it looks like D1, when wing angle is at D1, it yields the best quality of airplanes. So if you were to present this to management, you may want to say, oh, well, when wing angle is at D1, the mean is the highest and standard deviation is the lowest. It seems like if we can only change the wing angle of the plane design, we might want to lean towards D1. We're not going to ask you to do this in this sheet, but this is one of the reasons why pivot tables is so critical, because it helps you to grasp the most important information in order to make important decisions. So moving on. In the last one, we're going to further organize the table and the data in a different way. So the highlighted part is from the book, so you should have that, and someone on your team should already be in the room constructing this while you're collecting data outside. So after the data is extracted from the pivot table, just like this one, try to take a mental picture of when weight location is at A1, A2, and A3. The average mean starts from 20.33. So we'll go back here. Look, 20.33 is right here, and so is the rest of this column right here. So what it means is that this summary table kind of showcases the data a little differently than before and uses the pivot tables that you have just made, to put the averages of means into the distance means cells, and then the standard deviation means, which are right here. So if you remember, this is 2.06 and so on and so forth. So this is 2.06. So it just grasps the critical information you have extracted into the pivot table and put them together all in the summary table. And the reason it seems very trivial that we're just moving data around and displaying numbers differently as how it looked in the previous 2 sheets, but it's actually a very, very important thing and practical thing to do in the real world. Because if you just have a bunch of data laying out like this and not even having mean or standard deviation, yeah, they're data, but it's very difficult to visualize and make decisions off of them. But if you just analyze them some and organize them differently, it will be relatively easier to make decisions based off of that. So in this question, we're going to ask you, hey, what design yields the greatest mean flying distance? And what design has the least standard deviation? So to answer them from this table, obviously, it's very difficult. But from this table, it's much easier because we can spot right away that A2 is the highest amongst the three options of weight location. For stabilizer, V3 is the highest, and for nose length, C3 is the highest, wing angle, G1 is the highest. So we can say that when we're only looking at the highest fly distances, we want the design of A2, B3, C3, and D1. But if the criteria is looking at the lowest standard deviation means, we pick out the lowest standard deviations. I won't do all of it, but you can see that we're picking the lowest standard deviations right here, like A1, B2, and so on and so forth. So that's how organization of summary data can help us make critical decisions. And last notes, again, remember to bring tape, any sort. That's easy to remove or easy to stick on. Or you can bring sticky notes too. So whatever helps you mark the floor, you can bring. And then paper clips for the weight location of your paper airplane models. And then after you're done, please bring everything back. Peel the tape off of the tiles and then dispose them properly. You should try to recycle the paper airplanes, and you can take the paper clips back with you. And then when measuring the floor tiles, remember the tile sizes are 1 foot by 1 foot, or you can say it's 12 inches by 12 inches. When you round, please round to the nearest half foot. It doesn't need to be very accurate, but the accuracy needs to be rounded to the nearest half foot. And the last thing I want to talk about is to cross-train. The reason why this is crucial from this lab on is because, as I mentioned before, you guys are going to be working as a team in this assignment, in the next associated assignment, as well as the final project. And all of these three assignments and projects are connected together around the Taguchi airplanes. So by cross-train, I mean you should have try to have all the team members at least toss some of the airplanes to get a feel of it. All of you guys should understand how to fold a paper airplane and how to fold them relatively fast and neatly, because during the final presentation, I will randomly choose from the team members who's going to toss the airplane and who's going to manufacture them and who's going to take down the time and flight distances. So it would leave you in a pretty difficult situation if your usual thrower is not actually picked at the final project. Maybe your time recorder ended up throwing the airplane and do not do as great a job as your regular thrower, and that could throw your grades down a little bit. So try to have everybody try out each other's role, at least just for a little bit, so to prepare for the final presentation. And I will try to bring the previous reports from previous semesters where students have done in the past to you. Maybe not this lab, but I'll remember to bring it on in the future couple labs for you guys to take a look at and to see the workload that you're going to face for the final project. Anyway, so for the Thursday lab, my students, I'll see you on Thursday. For the other labs, good luck as well. I will see you.